All right, so we're going to look at solving equations, and I want to just review briefly the process that we use for solving equations, and then I want us to relate that to a visual approach and what it means when we solve an equation. So on the left side of this equation, remember our first step is always to simplify each side, and you can see that on the left side there's some simplifying to do. I have 3 times a quantity, so I'm going to get rid of the parentheses using the distributive property. 3 sets of x plus 3 is 3x plus 9. And then I have some like terms on this side that can be combined. And the positive 9 minus 1 gives me a positive 8. So that first step of simplifying each side is complete. Then my next 2 steps is to get all the variables to one side and the constants to the other side. Or in other words, combine like terms, getting your variables on one side and your constants on the other. So I'm going to start by getting all of my x's on one side. So I add the opposite of 3x. You could have added the opposite of 5x. That's going to get me 0 x's over here and leave me with 8 equals 2x minus 6. Then I'm going to get all my constants together on the other side, making sure that there's none left over here with my variables. So I add the opposite of a minus 6, which is a plus 6. Leaves me with 0 there, and I get 2x equals 14. And then finally, that last step, step 4, is to multiply or divide to get that coefficient to equal 1. And so in this case, I'm dividing by 2 and getting a coefficient of coefficient of 1, getting that x equals 7. Now, it's always a good idea to go back and check your answer. Remember that what you're trying to find is the value of x that would make the two sides of this equation equal to each other, because that would make this true. So plugging in 7 on the left side gets me the expression 3 times 7 plus 3 minus 1. So I get 3 times 10 minus 1, or 30 minus 1, which is 29. On the right side, I'm going to get 5 times 7 minus 6, or in other words, 35 minus 6, which also gives me 29. So because the two sides are equal to each other, I can see that this, in fact, is the solution to this equation. It makes the equation true. Now, I have this right here, this equation graphed. And I've done this actually on this dynamic software where I can move this value around. So right now I have a vertical line where x equals -1. And you can see that when x is -1, if I come back over here and I plug -1 in each side for x, on my right hand side I get 5 times -1, which is -5, minus 6 gives me -11. So this point right here actually represents the input put in a value for x and the output, what I get out for this side of the expression. The same kind of thing happens over here. If you put in -1, I get 3 times -1 plus 3 is 2. And so I'm left with 6 minus 1, which is 5. And again, that's this point right here. When x equals -1, the output, when I put in -1 for x, I get out for that side of the expression, I get 5 out. And so that's its height. Now, as I come over here, when I move this point, or my x value, my input value, across the axis, you can see how when x is 0, the left side equals 8 and the right side equals -6. Both of these values are increasing, but the one on the right is increasing faster. It's a steeper line. And so eventually this point here will come up and meet with the other line. And that point where it happens is the point where both of them give out the same value, in this case 29. When I put in 7, I get out 29. And we actually found that over here when we solved the equation. If I put in 7 for x, I get out 29 on both sides. That is where they are equal. If I continue on, now the blue line, which is the right-hand side, which used to be smaller, now over here it is larger. And you can see that right here, that when I put in 10 for x, I get 44 out on the right, but I get 38 out on the left. And so as I get bigger than 7, I'm going to have here the right side larger than the left. When I go smaller than 7, I'm going to have the left side larger than the right. So that leads into this idea of solving inequalities. When we're solving an inequality, what we're trying to do is we're trying to figure out when one of these two sides is actually greater than the other. So if my question is, when is 3 times the quantity x plus 3 minus 1 smaller than 5x minus 6? Coming back here and looking at our picture, we can see that this side will be smaller whenever the red line is lower. So since this point right here was an x equals 7, this will be true whenever x is greater than 7. When x is bigger than 7, the red line is lower than the blue. If I was solving instead, when is the left side greater than the right? When is the red part bigger than the blue? Then I'm going to be looking for this section over here, when x is smaller than 7, because I know that they are equal when x is equal to 7. So we saw that again on this software as we moved the point along. If I'm over here where x is a smaller value than 7, then the left side is bigger than the right. So when x is smaller than 7, the left side is bigger than the right. Whereas if I move my point over here and use an x value bigger than 7, like 12, then you can see the right side is bigger than the left. So to make the right side bigger than the left, use an x value bigger than 7. Now, you're not always going to be using this kind of software to solve these problems. So instead, we're going to solve them algebraically just like we solved equations, except that we have to remember that we're dealing with not when are they equal to each other, but when is one of them bigger than the other. So let's start looking at some things that we can do to solve inequalities. Just like when we solved equations, we might add a positive or add a negative to each side, or we might multiply by a positive or multiply by a negative. And when we were dealing with equations, we could do any of those things and we would still get a true equation. So let's look at what happens to an inequality. Let's start with a smaller than b. For example, if a is -5 and b is -1, a is smaller than b because it's further to the left. Let's say I add 3 to each side. What's going to happen then when I add 3 to each side? Well, what's going to happen is I'm going to take both the value of a and b and make them 3 larger. 1, 2, 3. And if I make them each 3 larger, then a prime will still be smaller than b prime. What if instead I had added a negative? Like let's say I added -2 to both a and b. Well, I would start from where a and b was, which was right here, and I would then go 2 to the left. And again, if a was smaller than b, then my new value, a prime, will still be smaller than b prime. How about if I multiplied each of those numbers by a positive? Let's say I multiplied by +2. If I multiplied both a and b by +2, then my a value now, which was at -5, will now be at -10. And my b value, which was at -1, is now going to be at negative, I'm trying to separate these, is now going to be at -2. Let's just restart with some new points here. So my a prime now is going to be at -10, and my b prime is going to be twice the distance, twice -1, which means it's going to be at -2 now. So all that does is double its distance from 0. It didn't actually change their relationship. So a prime is still going to be smaller than b prime. But what happens if instead I multiply by a negative? If I multiply both sides by a negative, what happens to that relationship? Let's say I multiply both sides by, let's say I multiply by -2. When I multiply -5 by -2, I'm going to get +10. And so my a prime is going to end up over here. When I multiply -1 by -2, I'm going to get +2. So my b prime is going to end up right there. Notice that when I multiplied by a negative, what essentially happened was, because the sign switched, it changed over to the other side of 0. And when it did that, the one that was further away is now further to the right instead of further to the left. And so that relationship switched. And so we have to make sure that if we multiply by a negative, and the same thing would happen if we divided, we turn the sign, because that inequality relationship will reverse. So whenever we multiply or divide both sides of the inequality by a negative, we have to turn the sign around. Other than that, it's exactly the same as when I'm solving equations. I can add to both sides, I can subtract on both sides, I can multiply or divide by positives, and nothing changes. The only difference is if I multiply or divide by negatives, I have to remember to turn the sign. So I want you to pause the video right now and go through and solve these first 6 inequalities. Remember, deal with them just like you did if there was an equal sign between. So instead of thinking this side's greater than that, you can be thinking that they're equal. Just remember that if you multiply or divide on both sides by a negative, that side or that inequality is going to change. So we have to make sure that if we do this, we turn the sign. All right, pause and take a try on those problems. Okay, hopefully you've had a chance to go through and try each of these problems. We're going to do them just as if there was an equals here. So in this case, since there's a coefficient on x, I need to divide by that coefficient. Since what I divided by was positive, I do not need to turn my sign, and I get that x is greater than 5, which means if I looked at this on a number line, here's 0, somewhere over here is 5, and I want all numbers bigger than 5. To check this answer, 5 should make the two sides equal. So if I put 5 in for x, I should get that 15 equals 15. If I pick a number somewhere over here like 10, it should satisfy this inequality. It should make the left side greater than the right side. So if I put in 10, I'll get 30 is greater than 15, and that's true. So this one checks, and so we can move on. Now, same idea here. I have a coefficient, so I'm going to divide by that coefficient, which is -2. I have to remember that when I divide by a negative, I'm going to turn my sign, so the sign turns around here. 8 divided by -2 is -4. Now again, when I look at the solution to this, -4 is to the left of 0. So I'm going to put my -4 here. This is an open circle because it's not going to equal, and my x should be smaller. Again, to check this answer, I'm checking two things. If I use -4, they should be equal on each side. So if I put -4 in here, then I get 8 equals 8. If I pick a number in the shaded region, like -10, then it should make this inequality statement true, where the left side's greater than the right. So putting in -10, I'll get 20, and 20 is bigger than 8. So that confirmed for me that this graph and my solution is correct. Notice there's two things I'm checking. Is the endpoint right? Does it make them equal? And is the shading right? Does it satisfy the inequality? All right, we'll kind of go quickly through the next one here. If I subtract 3 on each side, since I'm adding or subtracting, the inequality sign won't change at all. Again, when I go back and test this, 9 should make them equal, and it does. I get 12 equals 12. And when I test a point that would be in the shaded region, something greater than or equal to 9 would be something over here like 10. It should make this inequality true, and notice I get 13, which is greater than 12. All right, the next one's a little bit tricky. Notice to get rid of this 5, I have to subtract it, not add it. If I added 5 to 5, I'd get 10. When you do this, this gets rid of the 5, but leaves you with a negative x. That negative x means -1x, not 2x's, but 1x. So I still need to divide by negative 1. And because I'm dividing by a negative, this is that point where I have to turn my inequality sign around. So when I turn that inequality sign around, now it says x has to be greater than negative 1. So negative 1 is here, 0 is to its right. I know that x equal negative 1 would make this true because I get 5 minus negative 1, which is 5 plus 1. And if I pick something where x is greater than negative 1, like 0, 5 minus 0 is 5, and that's less than 6. So I know that this one works. All right, moving on to the next problem here. It says x is divided by 3, so I'm going to undo that by multiplying. Even though this number is negative, what I'm dividing by is not negative. What I'm multiplying by is not negative, so I'm not going to turn the sign. Again, to make sure that you've done this right, here's negative 15. Somewhere over here is 0, and I need to be greater than or equal to. So I'm shading to the right, bigger numbers. Negative 15 divided by 3 is equal to negative 5. And a number in my shaded region like 0, 0 divided by 3 is 0. 0 is greater than negative 5 because it's further to its right. So we know we got that one right. All right, the one that throws everybody off, there is a fractional coefficient. I could divide by negative 2/5, but that's always awkward for people to do. So instead we multiply by the reciprocal, because remember, dividing is the same as multiplying by the reciprocal. So when I multiply both sides by the reciprocal, this gets me a 1x. Notice the reciprocal was a negative number, so I have to turn the inequality. And because I'm multiplying by a fraction here, I'm going to write this one also as a fraction. I can simplify. 8 gets divided by 2, goes in 4 times, leaves me with negative 20. So as I check my answer here, if x equals negative 20, I'd have negative 40 over negative 5, which is positive 8. So that would make them equal. And then checking a point in the shaded region, x has to be bigger than or equal to. So fill it in and shade to the right, bigger values. Something like 0 should make it true because it's in my shaded region. So 2 over negative 5 times 0 would give me 0. And 0 is less than or equal to 8. All right, you have one more problem left to try. Notice this one's a little bit more complex, but it's the exact same thing you did with equations. So just like if there was an equals between the two sides here, you're going to first simplify each side. Then you're going to gather all your variables on one side, and then you're going to gather all your constants off to the other side, and then you're going to get that coefficient to equal 1. The only thing you have to remember is if you multiply or divide on both sides by a negative, turn that inequality. All right, why don't you pause this and give it a try. Okay, welcome back. We're going to try simplifying first. Notice both sides could use some simplifying here. On the left side, I have a 3x minus 5 times this quantity. So because I'm subtracting 5 sets of it, I'm going to change this to add the opposite and distribute in a negative 5. So this says 3x plus negative 10x, and then the negative 5 times the negative 4 here gets me a plus 20. And then my like terms gives me a negative 7x plus 20 on that side. On the other side, it says 5x subtract this quantity. So I could either think of distributing the subtraction, or I could put the unspoken 1 in front and change this to add the opposite, so that I can distribute in a negative 1. It now says 5x plus negative 2 plus negative 1x. And combining my like terms here gets me 4x plus negative 2. So both sides now are simplified. So now I can start getting all of my variables on one side. I'm going to subtract 4x from each side to get them off of the right side. And that gets me no x's over here, but leaves me with a negative 2. On the other side, this gets me negative 11 x's plus 20. Now that all my variables are on the left, I'm going to bring all my constants to the right. So I want to get rid of this positive 20 by adding its opposite. Since all I've done so far is adding and subtracting, I don't have to worry about turning my sign. This leaves me with negative 11x over here and negative 22 over there. Now, my last step is to get that coefficient to equal 1. So I'm going to divide by the coefficient, which in this case is negative 11. And since I'm dividing by a negative, I'm going to remember to turn my inequality sign around. Now, the check on this one is a little bit more involved because it's a more complex expression, but the same idea still applies. I'm going to first check to see that my endpoint makes the two sides equal. So if I put in 2, I'll get 3 times 2, which is 6, minus 5 times, and then putting in 2 here gets me a 4 minus 4. Now 4 minus 4 is 0, and 5 times 0 is 0, so I'm left with 6 minus 0, which is just 6. This should equal what I get on the other side. So on the other side, I have 5 times 2, which is 10, and then it says minus, and then 2 plus 2. 2 plus 2 is 4, and 10 minus 4 is 6. So there's my verification that my endpoint's right. Now I want to know that I've got it shaded right. And so testing a point over here in the shaded region should make the left side bigger than the right. So if I plug in 0, that's going to get me 0 minus 5 times 0 minus 4. Or in other words, a negative 5 times a negative 4, which gives me a positive 20 over there. When I plug in 0 to the other side, I get 0 minus 2 plus 0, which is just 2. And so I end up with 0 minus 2, which is negative 2. Now remember, I was looking to see that the left side was greater than the right side. And that is, in fact, a true statement. 20 is greater than negative 2. So I know that not only is my endpoint right, but my shading's right. So hopefully you've got a better feel for how this works. If any of these problems confused you in the least, please go back and rewatch those problems and look for other resources if that doesn't help. Just remember, solving inequalities is the same as solving equations, except for one thing. And that's if you multiply or divide on both sides by a negative, that's going to switch or turn that inequality sign around. But always remember, you can solve it with an equals and then just test one side. You want shaded the side that makes it work. Good luck.